Hello and welcome. In today's world, our data is literally everywhere at once, on our phones, in the cloud, across continents. But have you ever stopped to think about how all those copies stay perfectly synchronized? That is the fundamental challenge we're tackling today, the world of consistency in distributed systems. Think about it for a second. When you update a shared document, how does the system make sure your colleague, who might be halfway across the globe, sees the exact same change that you just made? And at the right moment? Well, that's not magic. It's the incredible challenge that consistency protocols are designed to solve. So let's dive in and see how they actually work. Okay, here's our game plan. First, we'll get to the heart of the consistency dilemma itself. Then, we're going to explore 4 key strategies to solve it, starting with a flexible model called continuous consistency, then moving to more structured approaches like primary-based and replicated write protocols. After that, we'll look at cache coherence protocols, the ones that make your daily browsing so much faster. And we'll wrap it all up by comparing the trade-offs, so you'll know exactly which tool is right for which job.
So, to make our systems fast and really reliable, we create copies, or what we call replicas, of data, and we place them closer to users all around the world. Now, this is fantastic for performance, but it immediately creates a brand new and very difficult problem. How on earth do you keep all of those copies perfectly in sync?
And this is where things get tricky. There's this constant battle between correctness and performance. If we're super strict about keeping everything perfectly updated all the time, well, the whole system can slow down to a crawl. But if we're too relaxed about it, users might start seeing outdated or just plain wrong information. This, right here, is the consistency dilemma.
So, how do we start to solve this? Well, our first approach begins with a pretty simple realization. Not every single application needs perfect instant synchronization, and this idea is the foundation of something called continuous consistency, a really flexible and often highly efficient strategy.
The really big idea here is defining what we call bounds. So instead of demanding absolute perfection, this model lets us decide what level of inconsistency is actually acceptable for our application. It's all about setting clear, manageable limits on just how far out of sync the data is allowed to get.
And we can set these bounds in a few key ways. We could limit staleness, for example, deciding that the stock prices on a display can be no more than, say, 5 seconds old. We could limit numerical deviation, maybe saying that 2 weather sensors in a field can't differ by more than 1 degree. Or we could limit ordering deviation, allowing perhaps a few chat messages to appear slightly out of sequence. It's a very practical trade-off, really, prioritizing performance where absolute perfection just isn't necessary.
But what if you do need stronger guarantees? What if close enough isn't good enough? For that, we turn to a much more structured approach, the primary-based protocol. And the core idea here is incredibly simple. Establish one single source of truth. In this model, one replica gets designated as the primary, or the master copy. So if you want to change the data, any request must go through this primary first. It acts like the ultimate gatekeeper, making sure that all the updates are processed in a really controlled, sequential way. The best way to think about this is like a group project, right? You don't just edit your own copy and then hope for the best. Of course not. You send your changes to the person who holds the master document. They incorporate your edit, and then, and only then, the new official version is sent out to everyone else. This is exactly how primary-based protocols prevent chaos.
Now, there's a really clever twist on this called the local write protocol. What if the master copy wasn't stuck in one place? Here, the status of being the primary actually moves to wherever the updates are happening. This can be incredibly efficient because it lets a process make lots of rapid changes locally before it has to sync up with everyone else.
So the advantage is really clear. You get simplicity and very strong consistency. All the writes are funneled through one single point, which makes the whole system state easy to understand. But that single point is also its greatest weakness. The primary can become a performance bottleneck. And even worse, if it fails, all write operations might just grind to a halt until a new primary can be found. Okay, so if that single point of failure is a deal breaker, what's the alternative? That brings us right to our next category, replicated write protocols, which take a completely decentralized approach. So instead of having a single primary, a write operation is sent to multiple or sometimes even all replicas at the same time. This is often called active replication. But the huge challenge here is making sure that every single replica performs these operations in the exact same order. If they don't, their data will just drift apart into chaos.
I want you to picture this.
Imagine an intercom broadcasting instructions to a room full of scribes. As long as every scribe hears the instructions and follows them in the exact same order, every single one of their books will remain identical. But if just one scribe misses a command or gets the order wrong, their copy's ruined. That coordination is absolutely everything.
So you can see we have two completely different philosophies for writing data here. The primary-based approach is centralized and much simpler to coordinate. On the other hand, the replicated write approach is decentralized and more resilient, but all that power comes at the cost of much more complex coordination to keep every replica in perfect sync.
All right, for our final category, we're going to talk about something that you deal with every single day, probably without even realizing it. Caching. How do we make sure that the temporary data stored on your local device stays consistent with the main server?
You know, when you visit a website, your browser often saves or caches parts of it. This is to make it load much faster the next time you visit. A cache coherence protocol is simply the set of rules that make sure this local, temporary copy doesn't become stale and start showing you outdated information.
Now, servers handle this in two main ways. The first is invalidation. The server simply tells your device, hey, that copy of the data you have is old. Just delete it. You'll have to fetch a new one next time. The other strategy is update propagation, where the server proactively pushes the new, updated data out to the cache. And the best choice always depends on this crucial balance. How often is the data being read versus how often does it change?
So we've covered a lot of ground, looking at 4 very different approaches to consistency. The crucial point I want you to remember is that there is no single best protocol. It is always a game of trade-offs, and the right choice depends completely on the needs of the application.
Let's just pull this all together and see how they stack up. Continuous consistency gives you fantastic performance, but only if your application can tolerate a bit of a delay. Primary-based protocols are your classic choice for simplicity and strong consistency, which is why you see them in so many databases. Replicated write is complex, no doubt, but it's the champion when it comes to fault tolerance and high availability. And finally, cache coherence is the specialist, designed specifically to make our everyday browsing faster by cutting down on server load.
So as we wrap up, I want you to remember this. Consistency is always a balancing act, a constant negotiation between performance, availability, and correctness. And that slight delay you might experience online, well, that's often the hidden work of a distributed system doing its absolute best to keep its promises and to make sure the data you see is the data that is right. Thanks for watching, and see you in the next session of this series.